Swayam Prabha. Digital India. Educated India.
Welcome to this subject, Advanced Digital Image Processing and Computer Vision. Today, we will discuss on a new topic, that is on image transform. So, if we consider an image as a function over a space, for example, since we are dealing with two-dimensional form of images, so we consider a two-dimensional space. So, as we have already discussed, it's a some distribution of certain measurable entity, for example, brightness value, and you can represent the function as function of x, y, where x, y is a point in a two-dimensional space. We have denoted it by r square, that is the Cartesian product of two real spaces. So, which denotes this space. So, when we would like to describe this image, so this is the original description as a function over that space. But this image can be described in other form also. For example, if I have certain set of known functions or given functions, which we are calling here say basis functions. So, then with respect to that set, can I describe an image? Mathematically, we can consider a particular form, that is the linear combination of these basis functions, which can describe an image. So, it is equivalent to a linear combination of these basis functions. So, I can write this image. So, this is the definition, this is a consideration. So, this set could be finite or infinite, and there could be ordering of these basis functions. So, we have certain indexes and certain kind of ordering, it may have certain ordering in the space. And also you can note here that the functional value, it could be a real number or a complex number. So, R is a set of real numbers and C here is a set of complex numbers. So, as I was mentioning that a linear combination of these basis functions which may provide as an image, that could be written in this form. So, we can see that lambda I is the coefficient for the ith basis functions in that linear combination. So, this is a mathematical form. So, if I know this set of coefficients which correspond to some basis function. So, if I can index these coefficients to the basis functions. So, this set of coefficients itself will be sufficient to describe this image. So, it is an alternative description of an image, or we call this is what is the transformed representation of an image, or we call it image transform. That means, this set of coefficients are the image transforms. They are the transform of f with respect to the basis function b. So, as I mentioned, it is a set of these coefficients. Once again, coefficients are to be also tagged with the respective basis function. So, if we have an ordering in the set, so we can also arrange these coefficients with the same ordering. Now, this I have discussed with respect to a two-dimensional functions, but in two dimension this ordering could be also two-dimensional ordering. So, instead of a linear ordering, we can have a two-dimensional ordering, and as I was saying that these are the coefficients of transform. So, this indexing could be also multidimensional. For example, for a two-dimensional functions, it could be two-dimensional indexing scheme, which means I can express this linear combination using this kind of short notations, that summation operations over both the I and j indexes. So, one of the advantage, why should we do it? Because if we have this linear combination, then the properties of basis functions can be extended in the analysis, because you know this is the component of a function. So, if we can, for the known properties, because the basis functions are given and the fxy any arbitrary function. So, given functions property can be extended on the properties of, or projected on the properties of the unknown function. So, that is one advantage we have in this kind of representation. There are other advantages which I will discuss subsequently. Now, for our convenience, we will restrict our discussion initially to one-dimensional functions instead of two-dimensional functions, because we started with images. First, let us understand this kind of linear expansion for a one-dimensional function. Then we will see its extension to two dimension. So, in a one-dimensional linear expansion, linear combination of this basis function could be written in this form, where indexing, as you see, that just one dimensional index is sufficient, and we represent the basis function as Vix. So, there are few things, let me define some mathematical operations, because those operations could be conveniently used to obtain this kind of linear expansion. So, one of the operation is called inner product operation. So, it is in this operation, this is a definition. So, if you have two functions f and g, then you consider the integration of the pointwise product of the functional values. That means at x, but you should note here that one of them is a complex conjugate of the function of its original, of the function itself, which means here f and g and fx multiplied with complex conjugate of gx. So, that is how the inner product is defined to handle the complex number. And in the real function, of course, complex conjugate can be simply substituted by the function itself, because there is no imaginary part there. So, real part remains the same in the complex conjugate operations. So, this operation is called inner product, as I mentioned. And another set of basis functions, characteristics of a basis functions you would consider, which are which gives us convenient operations, mathematical operations for computing this linear expansion. So, one of this expansion is called orthogonal expansion, if the basis functions are also orthogonals from each other, for each pair orthogonal. So, what is this orthogonality? Let us also define that. So, we say two basis functions are orthogonal if their inner product is 0, when two distinct basis functions, but the self inner product will be a non-zero value. In fact, it will be positive. Actually, one of the interpretations, as I told, that if it is a complex number, then the number with its conjugate, you will get the magnitude of the complex number. So that is how you get it. I mean, square of the magnitude, I should say, of the in that polar representations. So you get a real number, and it will be always positive. It will be always because it is square. So the transform coefficients in orthogonal expansion could be obtained easily because of this property, that if I take the inner product of the function with a basis function, then I will get its corresponding coefficients in its linear expansion. Because if I take inner product in that linear expansion, so linearity rules applies for inner product operation also. So which means that I will consider inner product of that function with each and every basis function, but from the linear expansion only the basis functions for which it is taking the inner product. So that component will give non-zero value, and that too will be proportional to the corresponding Ci, what is shown here for the self inner product for the ith function. So it will be proportional. So we can write it in that case. So lambda I, because that Ci would be there and the lambda I will be also there. So we can write it in this form. So if I explain that why it is so, it can be shown that I can write f as I can write this f as sum of lambda I bi x, and then if I do the inner product, so this multiplied by bi star x dx, because linearity holds here. So this is what you are computing. So as you can see that bi star x is so if I expand it, it would be something like this. So lambda 1 b1 x bi star x, and it goes like this. There would be lambda I bi x bi star x, and it goes like this. So all these terms will be equal to 0 because of the orthogonality property. Only this term will give you Ci. So from there you get this expansion as lambda I Ci. So if you want to get lambda I, so you have to divide it by 1 by Ci. So this is the reason that why you get why you consider to take orthogonal expansion or orthogonality property of the basis functions for that basis set of basis functions. So another thing is that if Ci is equal to 1, it is simply the inner product. So you don't have to divide because Ci is equal to 1, and if your basis function satisfy this property, all the basis functions satisfy this property in your orthogonal set, then we call that set of basis functions also orthonormal basis functions. So simply I can compute lambda I as the inner product of function f and bi. So this lambda is, as I mentioned, they are the transform of the function, and this operation is called forward transform operation, or we can call it as a forward transform. So from lambda I we can reconstruct fx, because you can then compute once again the linear combination, which means that the inverse transform would be simply lambda I bix di. I mean here I have shown in the continuous form as if I is varying continuously. For a discrete form, again the summation would be used. So one of the examples all of you may be knowing that Fourier transform, and if you can check with the Fourier transform expression, how do you compute it? Actually, you have this set of basis functions which is called base of the Fourier transform, is given by the set of complex sinusoids, which is given here in the form of e to the power j omega x, as you can see here. And you can have the orthogonal expansion, and you note that this set is infinite in this set. Omega varies continuously, infinitely. So theoretically, if I consider that we have all infinite number of coefficients because of this expansion, I should be able to reconstruct back the full function. So that's why we call it complete base, because we can get the full function from here itself. And the orthogonality property of this function is given by this particular expressions. We can show that with this expression. So any two non-distinct inner product of any two non-distinct sphere would be 0, or otherwise it would be twice pi delta naught. So that is what is orthogonality property. And then this is a unit impulse function. Delta is a unit impulse function, just to explain that part. So Fourier transform expression would be, as now you know that it should be inner product of the function and the individual basis function. So e to the power j omega x would be e to the power minus j omega x in the complex conjugate form. So this is how the Fourier transform expression looks like. The inverse transform will be given by this. So there is certain scaling factor associated with this transformation. So it's orthogonal, and that 2 pi is there, as you can see. So it is not 1, it is not orthonormal. So while doing the inverse, it is 1 by 2 pi. So if I say 1 by 2 pi of e to the minus j omega x, then that becomes orthonormal function. So the full reconstruction would be possible, as I mentioned, because of the property of you have all the functions from these relations. Another interesting insight of this transform, what we can see that as this complex number, any complex number expressed in this form, exponentiation form, can be expanded into the real and imaginary part in this way. E to the power minus j theta is equal to the cos theta minus j sin theta. So this transformation, Fourier transformation, can be written in this form. So one of them will have cos components. The real part will have the inner product with the cosine of that functions, cosine of certain cosine of with the frequency function, cosine functions, and imaginary part will be the inner product of the sine functions, and of course the negative sign is there. So there is a real transformations and cosine transformations and sine transformations, but both are required. And interesting part is that this basis set of basis function itself is orthogonal. This is also orthogonal, and if you take the union of them, they are also orthogonal. So this set of basis functions, though they are orthogonal, they are not sufficient to give you back the full signal. So orthogonality does not ensure that you can have full reconstruction of the function. It could be partial reconstruction. So when it is possible that the set is also orthogonal and also it gives full reconstruction, then we call that basis set as a complete base. So that is what I have mentioned when I said that this set is complete, but this set and this set, though they are orthogonal, they are not complete. But there are certain functions where it is possible to reconstruct them only with the cosine basis functions or only with the sine basis functions. So those functions are called even and odd functions. So we know already that when Fourier series analysis, when you have a periodic signal, then for the even periodic signal, it is only the cosine harmonics will be there. For odd periodic signal, it is only the sine harmonics would be there. It is the similar thing what is happening, what is considered here. So just to tell you that when we call a function as even function, so this is a mathematical definition. So if I take the negation of x, you will get the same value, which means suppose I have the functional representation. This is my x graphical representation. So, and this is the origin. So if I have a value here which is displaced by certain distance, say t, then in the negative part, if I take minus t, I will have the same value here. So this is called even. So the functions, like as you know, the cosine functions, they are also even functions. So the even basis functions are reconstructing a even function. So that is the way you can interpret. Similarly, for odd functions, you have this property. That means f minus x equals minus x, which means once again, if I show it graphically, so if I have this functional value here, here the functional value with t. So, if I take minus t, then this functional value would be the same, magnitude would be same, but it would be negative. So, the 0th point, because it does not have any sign. So, 0th point would be 0. So, that is also another feature of the odd function. The function value at 0 is already defined, it is 0. As you know that sine function, so for a sine function, it's a, if I draw a sine function full cycle, it will be like this. So, for a sine function, the it is also an odd function. So, as I was telling that odd functions are reconstructed by this kind of odd basis functions. So, so this is possible because you know that this is true for even functions. If I take the inner product with sinusoids, it would be 0, and for odd functions, the inner product with the cosine function is also 0. We can prove it also with with this expansion of cos theta in terms of exponentiations. You can show it by Fourier transform analysis itself, and this is a sin theta expansion. So, this is the this is the conclusions of this discussion, that if we have the even functions, then full reconstruction is possible with cosines function, cosines basis, or if you have an odd function, then full reconstruction is possible with sines basis functions. So far I have discussed about the continuous form of representation of a function, but let us discuss the case of discrete representation, because that is what is our context. We are handling discrete representations of signals and images, particularly images in our case. So, in one dimension, so discrete representation of a function can be, as you know, can be considered as a sequence of functional values with regular intervals. So, it is sampled sequences, where you can see that in this case, this x naught is the sampling interval, and in nx naught will give you the respective. So, finally, in abstract sense, I have only a sequence position by which I denote the corresponding functional value. So, as I mentioned, this is a sampling interval, and this set is a set of integers, that is in my notation, just I have explained here. So, in that case, you can consider the representation of this kind of sequence of values or numbers. They can be considered as a vector, and if you have an infinite series, infinite sequence, it could be infinite dimensional vector space. But mostly, I mean, as you know that in practice, when you are computing, you work with finite representations. So, we have a finite representation of a sequence. So, we represent the sequence in a finite dimensional space. So, a sequence of length n can be represented either in the form of a sequence or can set of ordered numbers, that is the sequence, or I can represent it as a vector. In the vector notation, I have used that column vector notations, and which means I will show the vector as a row. When I am showing in the row arrangement, I will be using this transpose operation to denote that actually essentially it is a column representation. So, when you are working with mathematical expressions, operations, your convention needs to be explicitly defined, and with respect to that, all operations are subsequently expressed. So, that is why it is important to understand that what kind of representation of vector you are considering. So, this representation effectively, which means in the linear algebra form, this could be written in the matrix from F0, F1 to Fn minus 1. So, effectively this is what is the representation of this vector. So, when you are considering a transformations, first the matrix multiplication with proper dimensional specifications itself is a linear transformation. So, let us try to explain that part. You consider this particular matrix multiplication. Say this is your n cross 1 vector, which is a column vector, and which is your the corresponding functional representations, as I was mentioning. So, x is that input vector and which you are representing, and this is a transformation matrix and whose dimension is n cross n. So, if I multiply this vector, column vector, with this transformational matrix of m cross n, I will get another column vector of size m. So, this is what is transformation. So, I have a n dimensional vector and then I am transforming it to a m dimensional vector. So, this is the linear transformation. When m equals n, then this matrix also becomes a square matrix, and if it is an invertible, then you can completely recover the vector x, compute x from y, because you just apply the inverse operation. For a square matrix, that inverse exists if it is non-singular, then you can get it back. So, that is what. So, it has its inverse transform if B is a square matrix and invertible. So, when we talk about now basis vectors, so that transformation matrix B is the matrix which is actually giving me basis vectors. So, what are they? Actually, each row of that basis vectors, they are representing, each row of that matrix, they are representing a basis vector in the column form. Because you are doing, if you see that in the matrix multiplication, what you are doing, you are basically taking the dot product of the row with the column if they are real numbers. Okay. So, it is a dot product with the dot product, basically it is a dot product with the row and column. If I say it is row vector and the column vector of x. So, that is actually the inner product in the vector space, that is the inner product. But so, when we specify this transformation matrix, we will be considering the basis vector should be also should have the complex conjugate form. So, which means that the rows what I said, those are column vector, but complex conjugate of those rows are the column vectors, they form the basis vector. So, I can so I have said rows of B are called basis vectors. Basically, it is a complex conjugate form of the basis vectors. So, I can write the expressions. So, in the submatrix form, this is another representation I will be using in my subsequent discussions. You can see that these are all vectors, and by putting them transpose operations, I am showing that representation is in the row form, because my normal representation of vector is a column vector. So, when there is a transpose, which means it is a row. And then I have also considered the complex conjugate operations in this, which means my basis vector is B0. Basis vector is B0, B1 to Bn, and in the transformation matrix, I am converted them into the form of a row and taking a complex conjugate. Then you have those dot products of with the input vector. So, that is what you get. For the ith component, you get the ith basis vector, which means ith row of this transformation matrix, and then you take the. So, if I consider there is a input vector x, so it is doing this dot product, and that would give you the component, ith component of this consideration. So, this is the dot product or inner product, as I mentioned. So, the orthogonality condition is once again would be interesting, but as I said in this case, this function, as you see, so this should not be treated as well, this is a x, is a vector here. So, this I mean already if B is invertible, you can get back the function, that is not the point, but orthogonality function, orthogonality condition makes some of your computation simpler. So, where it is now, let us try to understand. I told that to get back y, so you are you are basically performing this transformation. You are getting y. You are getting y equals bx. This is the transformation you are doing. So, what you need to do to recover x, you have to get x equals b inverse y. So, this inverse operation is a computational intensive operations, but you can do it. But if you have orthogonal basis vectors, then this inverse operation becomes simpler. You do not require to perform explicit exhaustive inverse operations what otherwise you used to do for any arbitrary matrix. First, let us once again try to understand orthogonality conditions with respect to the set of basis vectors. It is similar. You can see that inner product of any non-distinct pair will be 0, and for a distinct pair once again it will be a non-zero and positive value. So, I should say also Ci should be greater than 0. So, Fourier transform, discrete Fourier transform is one example of this kind of orthogonal transformations, and you can see that the basis vectors are defined in this way. So, there are n basis vectors and k is a parameter. This k should have been small k. Here also this k should have been small k. Okay. So, this k is a parameter here. K by n corresponds to certain frequency component. So, k is a frequency component, if I say, and these are functions, and this is the forward transform operations. So, this is the inner product with this basis function. Since this 1 by root n is not taken here, so in the inverse transformation we have taken twice of that. So, 1 by n. So, if I use 1 by root n, I have to use also 1 by root. So, I could have written like this 1 by root n, and then this is also 1 by root n. This is the reconstruction part, as we have discussed earlier also. It is a linear combination. This is the coefficient, this is the basis vector, and then 1 by root n of this basis vector. But since this is missing in this expression, say so this is missing in this expression. So, here also this should be used. I mean, this should be the expression. So this is how the discrete Fourier transform is mathematically you can relate with our discussions with orthogonal expansion of a function. But usually to relate the discrete Fourier transform with the Fourier transform in the continuous domain, what you need to consider that how it is related. So, you know that Fourier series of a periodic function. So, if any periodic function you can get its Fourier series, and then you are basically getting the corresponding coefficients or coefficients of the harmonics in that form. So, here discrete Fourier transform is a for the sequence, it is a Fourier series of the periodic function. So, here some advantage we have in the discrete domain, I am going to discuss further more on this aspect. Suppose this is your sequence. Now, to transform this function to what we can do, so these intervals are not defined. These intervals are not defined. So, I could have used any definition, but when I am using this is as a period, this signal as a period, and these are the samples of a period, then I can perform a periodic extension of these signals. So, this is a periodic extension and this is a period. So, this period, as you can see, it is proportional to if the sampling interval is x naught, this period will be n x naught. Right. So, what is the fundamental frequency in that case? Fundamental frequency will be 1 by x naught, like for the Fourier series expansion, and then the harmonic of the fundamental frequency will be k by nx naught. But in the Fourier series, here you can see that if it is k by nx naught, here this time instant should have been also n into x naught. So, this x naught and this x naught, they get cancelled, and finally you get this particular operation. You get this expression. So, you get the k by n expression, and we call it a normalized frequency. So, just to summarize this discussion, let me put it that this is the definition for a periodic function, and where n is a periodic sequence. So, the sampling period is not shown, is not mentioned, and it is not required for that, but fundamental frequency, as I mentioned, is 1 by nx naught, and this frequency then it is called normalized frequency. This frequency is called normalized frequency because actual frequency would have been k by nx naught. Actual frequency would have been k by nx naught. And the other thing you should observe that even in this case, in this particular type of extension, the Fourier series what you get, or coefficients of Fourier series, they are also periodic, and that is why it is sufficient that if you have only n coefficients, and then you can reconstruct back the function. Mathematically, we can justify with respect to the transformation operations with the matrix multiplications. So in that case, so that is in the linear transform space, I am just coming to that. So this is the expression of the discrete Fourier transform. This is the kth component. Instead of y, I have written f, capital F, and this is the transformation. So essentially it means that I will be using this kind of matrix multiplication, where each row is the corresponding complex conjugate form of that basis vector. So this is the complex conjugate form of the first harmonics, and this is for the n minus 1th harmonic. This is the DC signal, and you can see that you are performing this expression, that is a dot product with each row and column. So for each coefficients, you take any particular coefficients f1, then this row and this column vector, they are the dot product of them will be giving you f1. That is what is expressed here. So it's a linear transformation. Now this is your transformation matrix. So this matrix is your transformation matrix, and in a general form it is also invertible. So if you can have its inverse, you can simply apply inverse and you can compute it. But since this set of vectors is also orthonormal in that sense, I mean orthogonal, because 1 by root n was there. So we can write it in this form, Fn, and then we can write it Fn inverse. Actually, this 1 by n is missing here. It should have been 1 by n. So this is the discussion. I mean, this is what. So the advantage here is that Fn inverse is simply the Hermitian transpose of F. What is Hermitian transpose? You, for any matrix with complex numbers, you take its transpose and then complex conjugate, take the complex conjugate of each element, which means this one, if I transpose, so the Hermitian matrix would have been something like this, that this column in the transpose form, it remains the same, it is same column. Then this column, it would be now row vector, but here you will have respective complex conjugate form. So j 2 pi say by n, and it goes like this. Okay, so this is the explanations for having set of orthogonal basis vectors. Then your inverse becomes simpler. You don't require to compute the inverse in this case. Now this I have talked about discrete Fourier transform, but there could be in the discrete representation, there are many other flexibilities. One flexibility I just mentioned, that since it's a finite sequence, so outside that interval you can have your own functional definition which will be convenient for transformation, but again you can, which will give you back the same finite sequence from its transforms. The other thing here, particularly for the discrete Fourier transform, we can look at the discrete Fourier, the basis functions of the discrete Fourier transform as a discretized form or sampled sequence from a sinusoid. So, in its original form of discrete Fourier transform, suppose you have a sinusoid. So, when I am sampling it, say I am sampling it, for example, this is my origin 0. So, I am sampling it at regular interval from these points, and these are forming my basis vectors. These are forming my basis vectors. But what I can do, instead of sampling from the point here, I will just give a beta shift. That means I will sample from, so if I give a beta shift, say my sample point would be this, all shifted by beta. So now the basis vectors what you get, that basis vector will not be same as the basis vector which are originally sampled from the from the 0th point of the sinusoid and then at regular intervals. Here there is a delta shift which is called phase shift of the sinusoid signal. So when you give this kind of shifting, we get a different basis vector, but if you do it uniformly for all of its harmonics, because in Fourier transform, so if I do it for all of its harmonics, then at regularly, I mean the same shift, they also give you another set of orthogonal basis vectors or orthonormal basis vectors. So given a beta shift, even you can do that, and not only that, since you are doing you are selecting some of the harmonics, there can be also shift in the frequency of selection, but again at regular intervals. So instead of saying 1 by n, 2 by n, I will say 1.5 by n, 2.5 by n, and in this way I can select my frequencies. They also will give you set of orthonormal basis vectors. So what is required is the set of orthonormal basis vectors, then the linear expansion becomes simpler. So this is the generalized discrete Fourier transform, and using the basis vectors, generalized form of basis vectors with parameter alpha and beta. So each alpha and beta corresponds to one kinds of discrete Fourier transform. The reconstruction is also in the same way, because they are orthogonal. You can simply use the respective basis vectors or basis vectors, and that would give you back the orthogonal functions. We give you back corresponding function itself. So for different cases of alpha and beta, we will have different types of discrete Fourier transform, as you can understand now. So when alpha equals 0, beta equals 0, it is the base case. It is the ordinary discrete Fourier transform expression what we get, and we call it discrete Fourier transform. When alpha equal to 0 and beta equal to half, we call it odd time discrete Fourier transform, because you are giving shift over the time. So when you consider a sinusoid, you are giving shift over the time axis. When alpha equal to half, beta equal to 0, we call it odd frequency discrete Fourier transform. The term odd, why it is odd, let us not understand at this point, but there are reasons why they are called odd. And then when alpha equal to half and beta equal to half, this is called odd frequency, odd time discrete Fourier transform. Their respective acronyms are also shown here. Those are the conventions which are used in the literature. So the inverse transforms also is possible, as I have mentioned, and the thing is that the advantage of this kind of orthogonal property, it's very interesting here, because the complex conjugate, because these are all complex numbers, I mean these are complex vectors, so their conjugate will be the Hermitian transpose, and which are related, these Hermitian transpose are related to one another of this generalized form of these basis vectors. Suppose this is a transformation matrix in a general form. So this is a notation I am using just to explain this notation. Say this is the matrix representation, the dimension of the matrix is shown here. So, K varies from 0 to n minus 1. So, K is along the row and n here small n. So, just index locations they indicate whether it is row index or column index. So, column index varies from 0 to n minus 1, which means this matrix is up from n cross n, and individual element of this matrix is shown here. Earlier also I have shown this representation, just now I am explaining it. So, if I expand this concise representation, it will be given me an n cross n square matrix where each knth element can be expressed in this form, and alpha beta is the parameter in this case. So, if I say F 0 0, which means it is the transformation matrix for the discrete Fourier transform. So, the relationships what we can find in this case, it is I have just shown you the relationships among all different kinds of discrete Fourier transforms which we have considered here, and you can see that for usual discrete Fourier transform, the Hermitian transpose itself is the complex conjugate of that matrix, of that transformation matrix. So, you almost the same matrix, only the complex conjugate form. Whereas, if I consider the inverse with this parameter half and 0, which is this is for the frequency. So, it is odd frequency time transformations. So, here we will find that Hermitian transpose is actually complex conjugate of the other transformation matrix. So, these are certain interesting relationships, and those are but the point is that you need not compute explicitly inverse as you compute for any matrix. You can simply use this relation to get its inverse and then apply it for reconstructing the signal from these transformations. So, I talked about this periodic extension. There is another kind of extension which will be made periodic, but first let us understand that even the single period can be defined in some extended form. Earlier extension, what happens that this sequence itself is repeated. So, that itself defines a period, but not now. What we can do, we can use some extension of this sequence at the other part, and then we can make and then that makes a period, and then after that it is repetitive. The advantage here is that you have the liberty of making that extension in such a way that this period could be either even period or odd period. So, I hope you can guess that why we should do it, because then if you have an even period, then only cosine transform is required, only cosine function. So, we do not require those type of complex basis vectors as we did for discrete Fourier transform. Or if we can make it odd periodic function through this extension, then only sine transformation is required. So, that is the advantage, and not only that, there are different kinds of extensions are possible to make it even and odd. So, the basic general terminology for this kind of extension is called symmetric or antisymmetric extension, because symmetric extension, with the symmetry you define the even and with the antisymmetry you define the odd cases. So, let us understand what is this what is the symmetric extension and what is antisymmetric extension. So, we consider this is the base sequence which I have just indicated there, and then this is one form of extension. I have shown it with examples. So, you have this base sequence, and then you can see that this becomes your point of symmetry, which is already a functional positions in the sequence itself. So, about a sequence value, that end value. So, if I say this is the value, say at 0th index, and this is at n minus 1th end. So, at n minus 1th point, you make the point you consider that is the point of symmetry, and then you repeat the signal, define the signal in such a way that they are symmetric here. We call it whole symmetry because the point of symmetry lies at the functional point itself. There is another kind of symmetry which is called half symmetry. That means your point of symmetry lies between these two functional values in the sequence after extended sequence. So this n minus 1th point is also repeated here, and so your number of samples in that period, it is actually different for number of samples what you have here. So the length of period in the extended sequence, length of period will be determined that what kind of extension you are doing for the symmetric extension you are doing at the end and at which end. So you have both possibilities. So you have this end and also this end. Suppose you make a whole symmetric extension here, you make a half symmetric extension here. That is also possible. So you can have whole, you can have half, you can have half whole, you can have whole half, all possible things. But each one will give you a even periodic signal once you make it a period and then periodically extend it. Similarly, for antisymmetric extension also you can perform in the same. Our purpose is to make it odd periodic signal. So that's why the whole antisymmetry you insert a value, functional value here, and as I mentioned that the 0th position should have value 0, and this is that 0th position. This is the origin kind. So you make a functional value, you insert a new functional value 0, and then you extend them. And this is called whole antisymmetry. And for half antisymmetry, you insert a functional value in between. And then if you make periodic extension, these functions become odd periodic functions. So with periodic extension like whole symmetry and half symmetry, you can make and in its both ends, you can make the function as even periodic function. So cosine transform could be there, and with antisymmetric it could be sine function. But you should note that after doing, so you can make also whole antisymmetry and whole symmetry, and you have to check that actually what kind of function it becomes, what kind of periodic functions, whether it is odd and even by carefully examining the structure. So I am not going to give you all the details, so you may go through the literature and you can also have your own homework on that in this regard. So the point is that is why in the discrete sequence, in the finite sequence I should say, discrete cosine transforms and discrete sine transforms, they exist. You cannot talk about cosine transform and sine transform for continuous sequences, which I just mentioned earlier, but for any arbitrary finite sequence could be completely recoverable using only discrete cosine transforms or discrete sine transforms, and those are there in the literature. The advantage here is that, as you know, cosine and sine functions, they are all real numbers, so you can avoid handling with the complex numbers. So it helps in your computation. So to further elaborate this part in a very brief way, that as I mentioned that types of symmetric and antisymmetric extensions at two ends of sequence, and then if you apply an appropriate generalized discrete Fourier transforms, it will give you respective some of the variations of discrete cosine transforms and discrete sine transforms. So one example I have shown here once again, say this is your base period, and then through your whole symmetric and whole symmetric extension at both ends, finally you will effectively get this is the period. So you can see you started with an interval length of 4, but actually the length of your period is 6 through this extension, and if you apply the discrete Fourier transform, then you get type 1 eventicity. So that is what you will be getting. Actually this even is considered as the period. So period is an even number, as you can see, and then this is the expression for type 1 eventicity. You can get this expression. You can see only cosine functions are used. So the period here is 2n. So, if you start with n plus 1 samples, not n samples. So, this 4 is n plus, so then 2n. So, 4n plus 1 means n here is 3. So, 2 into 3 is 6. That is how you are getting this period. And this is what your this definition of this alpha that is given. It is because of the normalizations of this basis function. In the similar way, you can get other kind of cosine transform, discrete cosine transforms. So, this is another example where you have half symmetry extension. There you can see that with this 4 base sequence, the actual length becomes, in this case also 4. So, actual length becomes 8. And if I use this odd time discrete Fourier transform there, so you get type 2 eventicity. Here also the length is twice n, periodic. So, that is why it is called eventicity, and this is the expression for that. For antisymmetric extension, you have to apply this kind of Fourier transform with the imaginary part, and you will get only DST, because see, imaginary part is the sine transform. So, you get discrete sine transform. So, you should note what is the period here. It becomes 2n plus. The period is, basically 2n is the period. You start with n minus 1 samples. You start with only n minus 1 samples, then you get 2n periods. For another type of discrete sine transform, it is half antisymmetry, like you get type 2 eventicity, DST, and this is the expression. So, in this way, there exist 16 different types of DCTs and DSTs, and but no, in our context, we will be considering mostly on type 2 eventicity and also sometimes type 1 eventicity because of the operations. So, type 2 eventicity is used for signal, image and video compression. So, we will see further that how this understanding gives us different kinds of interesting operations later on for image processing. So, let me stop here at this point today. Thank you very much for your listening.